big monitor over there and put my recorded one over here, then I'd probably still have the same problem. So here's what we're going to do today. Today we're still in 4.1. This is 4.1, part 3, right? And it's just using kind of that radian and degree measure to solve problems, right? Keep in mind that everything that you're solving today is going to have to be converted to radians, right? So no matter what, we need to convert to radians if they are not in radian form, right? Everything that we're solving needs to be solved in radians. Solve in radians, right? So if you have a distance around a curve or around a circle or a circular arc, is mostly what we'll be talking about here today, are circular arcs. Make sure they're in radian form. If they're given to you in degrees, make them radians. None of my sample problems are going to require you to convert them to radians. They're already in radian measure. But if they're not, you know how to do the conversion, right? If it's given to you in degrees, just multiply it times pi over 180 degrees and get your radian measure. What we're starting with today is we're going to be talking about linear and angular speeds. Huh? Linear and angular speeds. I thought I wrote that pretty. Maybe because I didn't dot the I. Is that what it is? Does that make it better? Okay, thanks. I'll try and write a little bigger if it's. I forget that your guys' screens are shrunk down and I'm watching it on a giant one. So we are going to consider a particle moving at a constant speed. Moving at a constant speed. Along a circular arc of radius r. Circular arc of radius r, right? A radius is always r. If s is the length of the arc, you remember we were saying that arc length is s the other day when we were doing the arc length stuff anyways. S is the length of the arc traveled in a time t. Now this is just the problem. We will go over all of this and how to break it down. Then the linear speed v. Now this isn't a word problem. This is just describing how linear speed works. And the linear speed v of the particle is linear speed v equals arc length, which we're saying is s, over time, which is t. Right? So what are we saying? We're saying that v, our linear speed, equals our arc length, s, over time. Right? So if we're given any two pieces of this, we can find the third piece. Right? If we're given the arc length and time, we can definitely find the linear speed. If we're given the linear speed and the arc length, we can find time. If we're given the linear speed and time, we can find the arc length. Right? Once more, if theta is the angle, in radians, right? We want radians corresponding to the arc length. S. Then the angle speed, well, then the angular speed. We use this like little W thing, which is like omega in Greek letters, but it's just a little W. Angular speed W of the particle is, here's our other formula. We've got our angular speed W equals central angle theta. This is just getting the formulas down, and I will explain them. Over time, which is t. So what we know so far, right? We know that we have our arc length equals the radius times theta, right? We talked about that before, right? Well, I think it was last week when we talked about arc length equals radius times theta. It's the only one I got to last week. And then now we have the linear speed, right? V. Ooh, that went somewhere I didn't expect. The linear speed V equals arc length over time, right? And now we also have that W, our angular speed, that's omega, equals theta over time. I'm going to give you one little piece of information as well. See how we have ST right here, arc length over time? Arc length over time is the same thing when you think about it as the radius times theta over time. Why? Because S equals R times theta. And that might come in handy for you at some point. So we have all of our bits and pieces, right? This one might come in handy too. V can also equal arc length. Oh, we already have that V. V can also equal radius times angular speed. Why is this handy? Because what if I have parts and I need to find other parts, right? And I don't know how to get there. If I know all of these, to me, this is the key right here. Right? This is all of your formulas that you're likely to need when you're solving these kinds of problems. right? I think it's a really handy toolkit to have. It helps to know things like S equals arc length, right? V, what is V? Linear speed. Uh, omega equals angular speed. We haven't even gotten into the questions, right? This is just information that's handy to always have in front of you. Theta is our central angle. This is just something to refer to when you're solving them, so that you know like what every piece of the puzzle means when you're doing a formula. It helps to know what every letter in that formula means. Central angle. What are we missing? R, radius, and T, time. Central angle we want measured in radians, right? So as long as I know these formulas and what each piece of them means, I can use them when I'm solving these word problems, right? So if I have a word problem, which I absolutely do, such as, let's see, example, the second hand of a clock. I like clock problems with this because it's where it's going to seem most familiar. The second hand of a clock is 10.2 centimeters. Find the linear speed of the tip of the second hand. As it passes around the clock face. I put a period there, doesn't need a period. Okay, so let's talk about this a little bit, right? We're looking at a clock. We're talking about a clock, right? First of all, let's talk about what do we need? We need the linear speed, right? And we already know that linear speed is v. So we need this v equals the r, the, why can't I remember that word all of a sudden? Radius times theta over time, or we need the arc length over time, right? We can do either of those things, right? So let's think about a clock, right? If I've got a clock and we're saying the second hand, right? We're only going to put the second hand in there. We got 12, 3, 6, 9, right? And then all the times in between. So say my clock hand, my second hand starts here, right? And it's going to make its way all the way around at the same speed, right? It's going like 1 second at a time, right? For a whole minute, it's going to go around. What we do know in terms of how it goes all the way around the clock, we know that one full rotation around the clock, right, is 2 pi, right? It's 360 degrees or 2 pi. So for it to go, if it's starting here, if we start here, for it to go all the way around back to here, we know it's going to take 2 pi rotations, right? It's going to take 2 pi per minute, right? Every minute it's going to go 2 pi, right? It's going to travel a distance of 2 pi every minute, right? So we know that we're going 2 pi per minute. So our theta, that angle that it's going, is 2 pi, right? The amount of time it takes to go that 2 pi all the way around the circle is 1 minute. What is our radius? Well, think about this. What are we measuring? It says, find the linear speed of the tip of the second hand. So it's saying that we're measuring that second hand, which is how long? Exactly, 10.2 centimeters, right? The second hand of the clock is 10.2 centimeters. So that radius, right, starts here, goes here. Our radius is the length of the second hand, right? And so our R equals 10.2 centimeters. We have all of the bits of information here. Now, I know that it's arc length over time, but it is also radius times theta over time. Why? Because radius times theta equals arc length. So here we can go. The linear speed, right? The v that we're looking for equals radius times theta over time. And we know the radius is 10.2 centimeters. And we know the theta is 2 pi. And we know the time is 1 minute. Right? I guess we'd probably have to write that as 60 seconds. Right? If we want it in minutes per second. So if I do 10.2 times 2 pi, I get about 20.4 centimeters. If I divide that by 60 seconds, I get approximately, that's what these little wavy lines are, is approximately 1.07 centimeters per second. Does that make some sense a little bit?
Yes.
So the trick here is to know your formulas, what each piece means. If it says, hey, we are looking for linear speed, well, linear speed is v. How can we find it? Well, we can find it by knowing the arc length over time. What do we know? We know that the arc length equals the radius times theta, right? Over time. Time's the easiest one to find. Sometimes we'll be looking for the angular speed, right? We need to know theta and we need to know time. So we can break these pieces up a little bit, right? Let's look at finding angular speeds. When we're finding angular speeds, we're going from the central angle. We're measuring the central angle and how that changes, how that grows over time, the distance it's traveled based on the angle instead of the arc length. In this case, we were looking at it in terms of the arc length. How far around the outside of the circle is it going per minute, right? When we're talking about arc length, we're talking about from the arc itself, how long is it changing per period of time, whether it be second or minute, right? In this case, we did per second. So when we're talking about angular speed, right, we'll do an angular speed problem. Right? We want to talk about our omega, right? Omega equals the central angle over time, right? This funky W that I can never draw equals theta over time, right? Central angle over time. So for our example, we'll say the blades of a wind turbine. You guys know what wind turbines are, right? Anyone's ever driven to Palm Spring and you see all those giant windmills? That is a wind turbine. The blades of a wind turbine. I can't even say that. Are 116 feet. Each one of those blades is like 116 feet. The propeller rotates. I know that's huge, right? Considering I'm only 5 feet. 15 revolutions per minute. We want to A, find the angular speed in radians per minute. And B, find the linear speed of the tips. So let's see if we can draw a picture. So our linear speed, right? Our angular speed we know is W over equals theta over T. Our linear speed, again, is going to be V equals the rate times theta over time, or just the arc length over time. So we have our formulas that we need, right? Let's look at this. What do we have? We have a turbine, right? This sucker, right? And it's got these spinny things. Usually it's like 3 of them, right? But it doesn't matter to us. And each one of these is spinning, right? And we only need to know the length of one. We want to find the angular speed in radians. So the angular speed that this is changing, right? We're talking about the change of the angle. And then at the end, we're going to go the linear speed of the tip. How fast is that tip going around? What do we know about the propeller itself? It rotates 15 times every minute. Right? That's what we know so far. So we know that one revolution is a circle, right? So one revolution equals 2 pi, right? And we know also that it revolves 15 times in a minute, right? So we could say that it's going to go 15 times 2 pi per minute, right? So 30 pi radians per minute. Right? That makes sense? 30 pi radians per minute. Yeah. Radians over time. I have my radians over time. What don't I have there? I know that angular speed equals our central angle over time, right? Our theta over time. And what do we know? We know that our theta at this point, right, is 30 pi, right? It's 2 pi 15 times, right? Over 1 minute. So, I don't know why I extended that. So, literally, our angular speed is just 30 pi radians per minute, right? That's not super difficult. We know the time on it. We know that we've got 30 pi radians per minute. That is our angular speed. We found part A. How did we find it? Well, we know that it revolves 15 times per minute. The length of one revolution is 2 pi, so we've got 30 pi radians. How often does that happen? Every minute. It kind of gave it to us, right? 15 revolutions per minute. All we had to know was that arc length to find out the angular speed on this one, right? So this is our part A. This is our answer to part A, right? 30 rads per minute. But what about part B, where we have to find the linear speed of the tip? B, we need to find V equals S over T, right? Our arc length over T, or rate times radius times theta over time. Well, we know certain things. We know our theta is 30 pi, right? We already determined that. Do we know our radius? Heck yeah, we do. It tells us right here the blade of a wind turbine is 116 feet. So our radius times theta is 30 pi, which is our theta, times our radius, which was 116 feet. Over time, well, our time is just 1 minute. So we could just keep it as 1. So all we're really doing is multiplying these two top numbers, and we're going to get, I should make these like this because we're going to get an estimated 10,000 933 feet per minute. Right? This is feet. This is minute. Does that make some sense?
Yes.
Play with your formulas. The best thing that you can do for you, have a little card with your formulas written on them right in front of you. So you can go, well, what are they giving me and what am I trying to find? Right? And how can I make these things fit together? Trying to decide if I even want to do the circular area, the arc of a circular sector. I kind of really do want to do that. I'm just looking at the time. We only have 10 minutes left. Can I get it done in 10 minutes? I can. I can do it. I'm going to speed through it. Area sector of a circle. What is that? If I have a circle, boom, and I have, say, something marked off in there, and I want to know what's the area of this space, right? That's what the area sector of a circle is, right? What's the area of this space? And the formula for that is the area equals 1/2 the radius squared times theta. This will be the easiest formula that we have, right? What do we need to know? We need to know big A equals area, right? R equals the radius. Theta, again, equals central angle, right? This angle right here is our theta. This radius is the length from this center, right? This would be a radius. This would be a radius. If we need it, this is S, but it doesn't look like we need it for this. What do we need? We need the radius and our theta, right? So if I have, say, this is the easiest one of the ones that we do, but it's also the most useful. Sprinkler on a golf course, right? That's their example they're giving. It's a good thing I don't have to come up with these examples myself. You know, but it only goes a certain length, right? And then it goes back. A sprinkler on a golf course. I don't know why I got to add that. I could have just said a sprinkler. Sprays water over a distance of 70 feet. The distance is our radius. I wish I could get that kind of a spread on my lawn. Right? It's saying that it's going to spray this length that is 70 feet, right? Here's my sprinkler. It's going to spray 70 feet in distance, right? And rotates through an angle of 120 degrees. Find the area of the fairway watered by the sprinkler. What is the area that's watered? Right? So it's saying, okay, here is my sprinkler. It's going to go 70 feet, right? It's 70 feet long. It's going to travel 70 feet. It is going to rotate 120 degrees. So we know that our theta, our central angle, is 120 degrees. We know that our radius is 70 feet. I have one problem though with this theta, which is that it is in degrees and I need it to be in radians, right? So I'm going to have to multiply that 120 times pi over 180 degrees, right? And I'm going to have to change this out, right? So I have 120 pi over 180, and I'm going to get 12 pi over 18. Gosh dang it. 18. Then I'm going to reduce that. Those are divisible by 6, and I get 2 pi over 3. So now I have it in radians. So now I can go, okay, well, this is 2 pi over 3 radians, right? So now what? Now all I need to do is figure out that area, right? So we know, what is our formula? A equals, excuse me, 1/2 r squared over theta. And we have all the pieces of this puzzle, right? We know that our theta is 120, 2 pi over 3. We know our radius is 70. And now we just have to do the math. We go 1/2 of r squared. Well, that is going to be 70 squared times theta, which is just 2 pi over 3. Do we do this in our heads? Heck no, we do this on our calculators. Break it up into pieces if you have to. But this is calculator math. Nobody expects you to be able to do this in your head, right? Once you plug it into your calculator, I do the tops first. I'd go 4,900 pi over 3, right? When you plug that into your calculator, you're going to get approximately 5,131 square feet. Pull out the pieces, make it not be a word problem anymore, right? Once we knew what theta was and what the radius was, this was an easy problem, right? We just had to plug those in to the formula and then put it in a calculator. So think about what they're asking for. And they'll usually tell you, right? They're saying, what is the area watered? Well, the only problem we have with area is that area of a sector circle or circular sector or whatever it is, right? So you're going to use that area formula. If they're asking you for angular speed, go up to your formulas, right? Where are they? Where's our little box of formulas? If they're asking for angular speed, go to your little chart of formulas and say, okay, well, angular speed is W, and that is theta over time. So I have to find my central angle, right? And figure out what period of time and then pull those pieces out. And then you should be able to solve these problems. I will have the problems up before I go to lunch today. I wanted to see how far we got before I actually put the assignment together. Like I said, I promise there won't be any more than 6 problems on the homework. That will be at most. And I'm going to try and pull out any that have like boxes to fill in because those seem to be a little bit more confusing than necessary.